Yes, here we are once again. It's the physics video lecture, psci 168, video lecture 29. And I brought the demonstrations with me that I was lacking last time, so I didn't want to get too far ahead of the game. So this is the Christmas pyramid. This is a steam engine, and what we're talking about is heat engines. So I'll just remind you that the heat engine takes thermal energy and turns it into useful work. So thermal energy, right, that's heat. We can just burn fuel and we want to get useful work out of it. So that's the whole goal. And I have to start off by making some excuses. There's such a breeze in this lecture hall that this thing is spinning on its own without the candles being on. Nonetheless, I should be able to demonstrate something of use here. So I'm going to start with this thing. The principle we discussed last time, the fact that there's a breeze in the room, pretty strong one, is just going to make things more interesting. Okay, but I'll still be able to make my point with any luck here. Okay, so you burn these candles, and that's releasing the heat. Okay. And you can see there's just so much wind in here, but I wanted to show the chimney effect. The chimney effect plays a big role in our whole discussion. So I have this paper tube, I can fashion a chimney, and with any luck I won't burn the place down. It's made of paper. So the reason we're here is to see the chimney effect and see if we get one. So I placed this machine in the chimney, and yes, we have success. You'll notice it really speeds up. Compared to what we had before. Okay, so I'll give you the reason for the chimney effect in a moment, but I just wanted to prove that there is one, and when we discuss the physics of it, it'll also be clear. But yeah, so this is a heat engine. We're burning fuel. Candles are releasing heat, and what the chimney does is it gives us a path for the air to take. Instead of just turning into a turbulent column of air, it actually goes up the chimney. Oh, I touched the walls. Here we go, once more. Good, just so you saw it, you can get your screenshots if you want. There's the chimney effect. Okay. So that's the Christmas pyramid. Now you guys know what you want for Christmas. Okay. Good, and the candles definitely make a difference there. That's the functioning Christmas pyramid. Put the chimney there and it speeds up. So that'll be crucial. Okay, so that was our first heat engine. And because it's a turbine, this is actually the basis of really sophisticated heat engines, even nowadays. Although, of course, this is just a fun little thing. And if you looked up Christmas pyramids online, you could get images of many of these different types. So good, that's one of our heat engines. And here's the second one. This is a functioning steam engine. I kind of gave the functioning of it last time, and I'm going to repeat that, but I want to get this thing going first. So what we have is fuel here. There's some solid fuel tablets. They burn. I put them in under here, firebox, and then there's a boiler with some water in it. In fact, there's a little window at the end, and you can see that we've got some water in here. And water's gonna boil, turn to steam, and the connection to the piston isn't via a long tube. The cylinder is mounted up here, so it's kind of a direct connection to the boiler, and it rocks up and down as we turn it. And then with any luck, we'll get this thing to go and it'll actually make the light shine, at which point we'll completely declare victory. So now to light that fuel, I could just use this thing. There we go, so we get the fuel burning. And we bring this under the boiler. Maybe the pliers are a good idea. Okay, this shouldn't take too long. And now we have to wait a moment. Get this one out of the way. It's done its duty. Christmas pyramid has done its duty. Okay, so we have water heating up in the boiler. That won't take that long. So we have Christmas pyramid. And it's got the turbine. Axis. It's a task that it's doing. And we have candles. Ready to go. Okay, this one I'll carry up to the camera just to show it. But first, we'll give it a kick. It'll pick up speed. It's just getting started. Tiny glimmer of light right there. So I'll bring it a little closer. So you can see it. Let's see. There we go. This is the end view. And bring it back up to the front here. Okay, there's our functioning steam engine. See what it looks like. All right. Yeah, so how do we turn this thing off? It does not have an off switch. And we have to just remove the fuel. And you notice it's still running because there was still some steam left over in the boiler. Okay, I call that a success. So now you really know what you want for Christmas. Okay, so go back to our sketches here. So we had our flame, and what we have is an air current, okay? Hot air rises, and that's what's driving the Christmas pyramid turbine. So what's the function of the chimney? What the chimney does, so I'll put a chimney on here. Put a bigger chimney on here. The chimney provides a real separation between higher and lower temperature air. Without the chimney, the rising air can just diffuse, okay? But what you do is you channel it and you have a real temperature, and so temperature difference, I'm already gonna write that in here, it's gonna play a big role. So down here we have the T sub H due to the immediately heated air, and up here we have T sub C. Okay, so the difference in temperatures is important. Remember, heat transfer goes between higher and lower temperature, and this is actually heat transfer by convection. So we have the fuel in the candles. The fuel is burning, and of course it's releasing heat by heating the air. And you know, we had those butter candles. I don't know if we ever discussed exactly what's going on there, so let's do that before we move on. So with a candle of wax or a candle of butter, it makes no difference. Now you've got the wick there, and now you have your flame, little blue, little red. Okay, you've got your flame there. So how is the fuel turning into thermal energy? The wick, well, the flame is actually melting and even vaporizing some of the butter, okay? So the butter that's liquid is coming up the wick, and it's actually being vaporized by the flame. So the combustion is of vaporized butter, and the wick just serves to make a connection to the fuel source and the flame. Okay. So make sure you understand that pretty clearly as to the purpose of the wick and the fuel source. If you just had a dish full of butter, you'd probably have trouble lighting it, getting it to burn, because it would be more difficult to vaporize it. Not impossible though, of course, you could get a dish of butter to burn also. Good, so we got the fuel burning, we've got the convection here, so let's even write that this is heat transfer by convection, and because it's heat transfer by convection, it requires a temperature difference, and the chimney allows us to really get a good temperature difference in this situation. What you'd find is if instead of the chimney, you just put something flat right above the top of the turbine, it won't turn at all. Okay? Because you'll interrupt the air current, and you'll also interrupt or you'll destroy the temperature difference. Good, so temperature difference is important, and we'll see that it's also important with our steam engine. So the second one is the steam engine. And beyond this, I'm going to ask you guys to go online and find different types of heat engines, which I'll give a list for. You can print them out, get some good images for your book. Okay. So the steam engine, you know, we had that boiler there. It's got a window in one end, as you saw, and we have fire underneath. So we're burning fuel, and these were solid fuel tablets. They're kind of burned now, solid. You know, they look just like sugar cubes, except there's some solid fuel. So fuel burns, we'll give it a little blue and red. And that is what's heating up the water inside the boiler here. So we have water. And when I fill that little device, I usually fill it about that much in the tank. You can barely see it sloshing up in the window there. But the boiling water is turning to steam. The steam is under pressure, and it's being brought over to a cylinder. Now I'm separating them on my picture here. The cylinder is kind of right on top of the tank, but bringing it over to this cylinder over here, which has a piston inside. And it's the high pressured steam here that's pushing against that piston, which via a connecting rod turns the wheel. Okay. It does it on this small model, and it does it on any steam engine. So this is the connecting rod, and this is called a flywheel. You see in pictures of old steam engines, they have enormous flywheels. And the reason is you need to get some angular momentum here so that the thing will move slowly. It'll push the flywheel clockwise, say, and then on the return stroke, the angular momentum on this wheel is enough to push the piston back. But only if you open a valve. So each time you have to open a valve here. So the valve opens and closes along with this moving back and forth in order to release the excess steam and lower the pressure. So release steam and reduce the pressure. Otherwise, it would take just as much work to complete the cycle as you got out from it. So you got work on the out cycle, and you would have to put just as much in. But if you release the pressure, then it moves back freely. Okay, and from the flywheel, you can hook it up to something here. We hooked it up to a little generator. We actually got some light. And when we get to electricity and magnetism, we'll discuss how these things function. So our discussion will be pretty complete. Good. So what do we have here? Connecting rod. Connecting rod, and then there's the flywheel. And this is the cylinder, and this here is the piston. So quite a bit to say about heat engines, and they're different types, but this is the start of it. Now, where is the temperature difference here? We have a TH in the boiler, so I'll go ahead and, because it runs on a temperature difference. So we have T8, let's see. We have TH, high temperature in the boiler, and this low temperature is actually the atmosphere to which the exhaust is being exhausted, okay? So TH in the boiler, that's the temperature of that hot steam, which is under pressure. And then TC, I have to put that here somewhere, equals temperature of the atmosphere, we'll just say. For now, we'll get a little more detail on that. So let's survey what we have here. We've got the two functioning steam engines and the heat engines is basic principle. And yeah, the flywheel's turning, hooked up to a generator. We're getting useful work out of that, without a doubt. Exhaust is important. Both of them need a temperature difference to function. This one needs it to maintain an airflow. This one needs the temperature difference in order to complete the cycle and bring the piston back to its initial position. So the work that we're getting is when the force times displacement to the right here. So we wanted to get useful work. So the work is equal to the force times the displacement of this thing being pushed forward. Okay. So for your assignment, we need to get pictures of these, but then other types of heat engines as well. So I'm going to erase the one on the left and get a little list of things that you want to add to your notebook. So we need images and certainly Christmas pyramid, you'll see that there are some pretty ornate large ones over in Europe. And this little toy steam engine, and there are interesting historical pictures of early steam engines that really just had one cylinder. You will find them where the motion is vertical and there's a rocker arm for the connecting rod. So steam engine, you know, plus historical ones. And then modern steam turbines. Now, generally I show a whole bunch of pictures of these things and kind of explain them one by one, but you guys are gonna look these things up, and by referring back to what we're doing and what's to come, you will understand them. So modern steam turbines. What we have here, and plus historical, you know, you could include some steam locomotives. There are still some places where a few steam locomotives for trains are still in service. That's not very common, but it still exists. These are what we call external combustion. External combustion because the combustion of the fuel is happening outside of the machine itself that's producing the work. Okay, combustion is outside of it. It was in the Christmas pyramid, you know, candles on the bottom. And the steam engine, the modern steam turbines, the same thing. Okay. And you know, I'll also add here jet engines. Kind of thing you see mounted under the wing of large commercial airliners. So, by the way, the jet engine doesn't necessarily count as external combustion. It gets more parentheses, okay? You guys figured that out. Now, what about internal combustion? Your automobile engines, all the way down to your lawnmowers and things, are external combustion. So you want to get some images of those things as well. And your automobile will have anywhere from 4 to 8 or more cylinders. This was a single cylinder engine. Now caught that, we mean internal combustion, sorry. Internal combustion for the automobile, so different kind. And what that means is that instead of bringing high pressure steam from outside, actually a little bit of fuel is brought into the cylinder and vaporized and then made to explode with a spark plug. Okay. So you're actually having combustion inside the cylinder, and that combustion releases heat and high pressure gas and pushes the cylinder forward the same way. It has the same property though, it needs a valve, and therefore you need to have exhaust. Okay. Valve eventually takes the hot exhaust gases out the exhaust pipe. So yeah, you want to know the difference between internal combustion and external combustion, just discussed right here, and get some good images and maybe some explanations to go with them of these different types of engines. And you'll see they all go back to what I've just discussed here on these 2-3 images that I put up on the board. Okay, so where we're going to go from there is an analysis of this heat engine in terms of the thermal physics that we've studied up until now. So we're going to bring it back in our formalism. Let's see now. Okay, perfect. Okay, so what do we have? We have the demonstrations, we have the principles here, how these things work, and we have your assignment of getting yourself enough image material that will illustrate what we've been talking about and what we will talk about. Good, so moving forwards, what we're going to do next is construct the really stereotypical schematic diagram that you'll find everywhere, and I'll take us through that. So this will be a schematic diagram of the general heat engine, of any heat engine. Good. heat engine, this is schematic diagram. The generalized heat engine. And here's how it looks. You draw a box, an arrow, circle, another arrow, another box, and another arrow. So what's going on here? This here is called the high temperature reservoir. The high temperature reservoir is where you're extracting your thermal energy from. Okay. And what you do is you have the high temperature reservoir deliver some thermal energy. So now this is QH, and we know that's an amount of heat, thermal energy measured in joules, okay, and it's delivered to the engine, which I'll say right there. And as I just had up on the board, the engine delivers some work. So it delivers some work, and that could also be measured in joules. Okay. But as we saw in both of our examples, and this holds true in all examples, you can't have a cycling engine unless you have some exhaust. And so some of that energy comes out at a lower temperature, Q sub C, and we say it goes into the low temperature reservoir. Okay, so this is the low temperature reservoir. For example, with our heat engine, with both the examples I had, it was the atmosphere. It was just the air surrounding the engine. It was the low temperature reservoir. Now, to locate these reservoirs takes a little doing sometimes, but the point is that we're getting thermal energy at a high temperature and we're giving it off at a lower temperature. And in the middle of that, we're getting some work out. Okay. So that's the schematic diagram for all heat engines. We'll just write for all heat engines. And this is why we did it. We wanted to get that useful work out. Okay, so far so good. So this is already pretty idealized, right? A couple boxes and a circle and a few arrows. In fact, let me label this a little more. So this QH, this is the thermal energy at temperature TH, right? And this is the thermal energy at temperature TC, which is less than TH. So that's the way we always do that. So the direction of the heat flow is according to the laws how it's supposed to be. This is sometimes called waste heat. Waste heat. But it's not wasted in the sense that you're just throwing it away because you're not paying attention. Okay, this is waste heat, and it's necessary for the functioning that heat be given off as well as taken in. Okay. So since that's a schematic diagram, it looks pretty ideal. So let's talk about the ideal heat engine a little more explicitly. What we're saying there is that these are all of the processes. They're covered by these energy quanta. So there is no extra waste, say there's no extra friction, there's no extra heat being given off except for here. You could say ideally it would be like a car where the engine doesn't even get hot because the only heat is coming out of the exhaust pipe. You ever put your hand behind the exhaust pipe, you'll feel it's pretty, it's warm. Don't burn yourself, but Notice it's warm. So the ideal heat engine, these are the only heat flows. So Q, H, QC are the only heat flows and energy is conserved, so I'm going to number these. Energy is conserved. So that's the first law of thermodynamics. And the first law of thermodynamics in this situation then would be the energy in, that's QH, certain amount of thermal energy in joules, equals work out plus QC. So that's a conservation of energy. Nothing wasted, there aren't any extra terms here. It's just energy in, you get work, energy out as exhaust, right? Good, energy is conserved. So those are the requirements. So I'll even add here explicitly no friction losses or anything like that. So that's definitely ideal if there's no friction. No friction, etc. that you would have in there. That's why we have these strict equations here. Okay, so with this ideal heat engine, there's the question of efficiency. So we're going to define the efficiency in a couple of ways. First of all, the basic definition, it's the work that you got out divided by the heat that you put in. Okay. Even from this equation here and the fact we know there has to be some QC, this number can only be less than or equal to 1. Okay. So we already have E must be less than or equal to 1. Okay, that's because of energy conservation. Okay, so that's the general definition of efficiency. I need some room here, I'm going to erase. We need the efficiency of the ideal engine. You know, I'm going to keep this equation here in front of us right now. So the efficiency of the ideal engine. Because this was the equation for the ideal engine. Use the same letter E, W over QH, but now I'll use this W right here. Subtract QC minus QH. Okay, so QH minus QC divided by QH, and simplify. QH over QH is 1 minus QC over QH. So this second version is also pretty interesting. This was your basic definition. If you apply it to the ideal engine, you see it's 1 minus something. So the smaller you could make this ratio, the closer to 100% you would get. You know, ideally, we would want all of the work from the mechanical equivalent of heat, but we're not going to get all of it. But the smaller we make QC over QH, the closer we are to 1. So that's the efficiency of the ideal engine. Okay. And I'll list those. Okay, so once again, listing these, we have E, W over QH. I can call this E sub ideal is 1 minus QC over QH, right? This is always referring to that schematic and the general process. So the question is, what is the maximum possible efficiency? And amazingly enough, we've put together all of the necessary ideas to solve this rigorously. Okay. What is the maximum possible efficiency for a heat engine? Okay. Maximum possible efficiency. And you know what? I'm going to leave it there, because I want a little more time next time. So I'm going to leave it right there. For now, your assignment is to get all of those images that we listed, and you know, put together some good notes for what we've done so far, and make sure you understand what we've done so far. And next time we'll use the law of entropy to figure out the maximum efficiency, and then we can discuss some further going examples of heat engines. We can kind of generalize the concept and see where else this occurs in nature. Good. So see you guys next time.